Although it's already something common seeing the way airplanes can fly and stay in the air, flying will always intrigue us. And it raises that good old question of how it's possible for an object much heavier than air, which in this case is the airplane, to be able to stay in the air. It's a much lighter medium, and from a human view, can't support something that heavy. However, by observing nature, specifically birds, along with many studies and a lot of trial and error in aviation, humans were able to understand exactly how something could stay in the air flying. In simple terms, airplanes fly because of the shape of their wings, the so-called wing profile. The upper part has a curvature and the lower part is less curved. This asymmetry causes the airflow over the upper part of the wing to travel a greater distance, resulting in a higher airspeed in that region. This higher speed creates a lower pressure zone on the top of the wing compared to the air passing underneath the wing, which moves at a lower speed and higher pressure. And it is precisely this difference in pressure between the upper and lower parts that results in the generation of an upward force, which pushes the wing, generating the so-called lift force, which keeps the airplane in flight. Not only is the wing profile important, but also the angle of attack of the wing in relation to the airflow. The greater this angle, the greater the lift force the wing will produce. And the smaller this angle, the less lift force will be produced. And the third and final element that completes this equation is the speed of the airplane. Without speed, there is no way for a wing to produce lift. And that's why airplanes have engines and perform a long and fast run before taking off. This moment allows a huge and considerable airflow to pass over the wing, producing lift while the airplane is still on the ground. You can observe this phenomenon happening during the takeoff run, since the wings of some airplanes flex slightly upward, and this effect is much more pronounced on the wings of the Boeing 787, which are made of composite material and because of that, flex considerably more at all times during flight. But why could bending be something fatal for any airplane? Well, if you didn't know, the fuel of airplanes is stored in their wings in a principle of aerospace engineering known as a wet wing. In it, the airplane's fuel tank is integrated into the structure of the airplane's wings. In fact, the wing itself is the airplane's fuel tank. This configuration is a complex engineering choice that involves aerodynamic structure, safety, and performance. It eliminates extra fuel tanks, which would otherwise add significant weight and reduce the airplane's efficiency. By nature, airplane wings are made of two main components. The spars, also known as spares in English, are the main structural elements of an airplane wing. They function like beams that extend from the root of the wing to the tip, arranged longitudinally. Their function is to receive most of the aerodynamic forces generated by the wing and transmit them to the aircraft's fuselage, being essential for supporting the flight loads and the weight of the wing. And the ribs, which are transverse structural elements that transmit the loads from the wing covering to the spars, maintaining the aerodynamic profile and the shape of the wing. In other words, it's the ribs that give the wing that curved shape, which generates lift. And given the way these two components are arranged to form the wing ends up being hollow by nature. Then some bright mind thought, if it's hollow, it can serve as a fuel tank. It sounds simple, but it changed the aviation industry completely. And studies proved that putting fuel in the wings would improve the plane's stability. It would improve the overall structural efficiency by counterbalancing the lift generated by the wings and the weight of the fuselage. It would reduce the complexity of the aircraft's fuel system, since the fuel can reach the engine essentially by gravity. It would improve passenger safety by placing the fuel away from the passengers. But how exactly can fuel in the wings be beneficial? The main reason airplanes carry fuel in the wings is because of weight and balance issues. All airplane cargo, including passenger weight and carry-on luggage, is carried in the fuselage. Checked baggage in the cargo hold, onboard food, and other paid cargo also stored in the hold. This concentrates all the weight in the airplane's fuselage, creating great tension and structural stress on the wings during flight. What if there were no way to counterbalance this weight imbalance? That is, the dense and heavy fuselage and the empty, hollow wings. What would happen is that the fuselage would be exerting a great downward force because of its enormous weight. Meanwhile, the empty and hollow wings would be pulled upward because of the lift force they generate, creating a great upward flexing of the wings, resulting in early structural fatigue in the area where the wings are attached to the fuselage, a region called the wing root. In addition to plastic deformations, which is when the deformation is permanent, and finally the breaking of the wing in mid-flight, since the wing would flex far beyond the structural limits for which it was designed. Additionally, turning would be very difficult. Fuel is one of the heaviest components in an airplane. On some long-distance flights, fuel can account for up to a third of the airplane's gross weight. In others, it can reach almost 50% of the airplane's gross weight. For example, the world's longest non-stop flight from New York to Singapore, which covers a distance of about 15,349 kilometers, is completed in 19 hours of flight by the Airbus A350 ultra-long range. It requires the aircraft to carry between 110 and 120 tons of fuel. That amounts to around 165,000 liters of fuel. Since the aircraft has an operational empty weight of about 135 tons, that means the fuel represents 89% of the aircraft's operational empty weight. To distribute this weight more appropriately, all the fuel is placed in the wings and another part goes into the central tank, which is located in the belly of the plane. Thus, the wings filled with fuel distribute the weight better and more evenly over the aircraft, increasing the rigidity of the wings, contributing to greater stability in flight and reducing the phenomenon of flutter, which is a dangerous vibration or oscillation that occurs in the wings under certain conditions and can lead to their failure. This issue of more even distribution of fuel weight in an airplane is so important that in some aircraft, such as the Airbus A380 or the Boeing 747-8 fuel, can even be allocated in the aircraft's horizontal stabilizers to better adjust the center of gravity during long-distance flights and provide greater stability to the plane. However, fuel consumption in airplanes occurs as follows. When there is fuel in the central tank, which is located in the belly of the plane, as well as in the wings, the fuel from the central tank is consumed first, and only after that is the fuel from the wings used. This reduces structural stress at the wing root by lowering fuselage weight as the central tank fuel is used. Only then is the wing fuel used. If this sequence is not followed, and if you start with the wings, the fuselage will become so heavy and the wings will flex upward so much that they could break in mid-flight. However, putting fuel under the wings creates two major problems for airplanes. The first is that the plane can no longer land with the same weight it took off with. In other words, the maximum takeoff weight is higher and exceeds the maximum landing weight. That's why, in emergency situations right after takeoff, the plane has to circle several times or even dump some of its fuel before it can land safely. To avoid damage to the wing root and structure in general, because they're full of fuel. To avoid overloading the brakes and to prevent increasing the distance needed to stop safely, which could lead to accidents. Another problem with putting fuel over the wings is when making turns. Airplanes carry absurd amounts of fuel to make flights. For example, a Boeing 737. Next generation usually carries around 4,800 76 liters of fuel. That means 3.9 tons of fuel in each wing, totaling 7.8 in both wings. In addition to the 16,273 liters of fuel, which is about 13 tons in the center tank. When part of that fuel has already been consumed, especially the fuel located in the wings, making turns could be extremely dangerous for the plane. That's because when making turns, tons of fuel would shift position, dangerously altering the aircraft's balance, thus the center of gravity. When banking, the lowered wing, for example, would cause all the fuel to move more toward the wingtips, making that wing extremely heavy. While the rising wing would have all the fuel moved more toward the wing root. This dangerous imbalance, combined with the torque it generated, could make it so the aircraft wouldn't be able to return from the turn to its normal position, leading to a loss of control and even the beginning of a spin. This is a dangerous condition where the plane enters an uncontrolled spin and spiral descent. There would be dozens of tons of fuel weight, shifting position every time a turn was initiated. This phenomenon, which is known as fuel sloshing or fuel oscillation, is more pronounced in partially filled tanks. And it can be triggered by other factors, not just by making turns. It can also happen during turbulence, acceleration, or deceleration. Besides the main problem of fuel sloshing, being the alteration of the center of gravity, it could also induce vibrations or dynamic instabilities. Repetitive fuel movement can create oscillating forces that match the aircraft structure's natural frequencies. And if the frequencies of both coincide and amplify each other, vibrations can occur, making the flight extremely uncomfortable. Another problem with the movement of fuel is the exertion of considerable forces on the internal walls of the wing, especially in large aircraft. These tons of fuel, moving uncontrollably, could deform or even cause the rupture of the internal walls of the fuel tank, leading to a major leak in mid-flight right after the plane has started a turn or is facing turbulence. This movement could also accelerate fatigue in the materials, like the aluminum sheets that make up the wings, in bolts and rivets, creating stress points that would lead to micro cracks and deformations, potentially resulting in micro and macro fuel leaks. In addition to damage to various sensitive systems inside the tanks, such as fuel pumps, pipelines, and several sensors. In other words, without an adequate engineering solution, storing fuel in airplane wings could be an imminent tragedy. How do airplanes keep wires away in practice? Well, the engineering solution to this problem is to divide and separate the fuel into smaller compartments using walls, which are called baffles. These baffles create sections inside the tank and break up the free flow of fuel movement, turning large portions of fuel into smaller portions that can move even less. This way, the baffles prevent the fuel from moving irregularly and changing the airplane's center of gravity. Besides preventing changes to the center of gravity, this division also concentrates the fuel and prevents the fuel pumps from running out of fuel, even when the fuel level is low or when the airplane is making sharper turns, which is extremely important to keep the engines running properly. The fuel tanks of large planes like the Boeing 777-A350 or 747 are large enough for several people to walk inside easily, and to allow mechanics to inspect them, but also to prevent the fuel from moving around excessively. These baffles have openings through which mechanics can pass to access other parts for maintenance. These openings also allow the fuel to move from one compartment to another, which is also extremely important. And every rivet, screw, nut, and the entire internal structure of the tank must be sealed to prevent fuel from leaking or seeping around these components. and the sealant for waterproofing it. It must allow the aluminum to expand and contract due to rapid temperature changes, and it must maintain its sealing properties when submerged in fuel and when left empty for long periods of time. The phenomenon of fuel sloshing and the use of baffles is also taken very seriously in tanker trucks that transport liquids like fuels. Since without the baffles, a sudden acceleration, a hard brake, or a sharp turn would be enough for the inertia of the liquid to make the truck lose control or even tip over. Especially because the truck is never completely full and the movement will be much more dangerous during sudden stops, since the liquid can come all at once and damage or even completely rupture the tank. Fuel sloshing is also a concern in rockets due to the enormous amounts of fuel they carry. In missiles powered by liquid fuels and in several other vehicles that experience high G-forces, like Formula One cars, which employ clever designs to address these movements.